We will now look at a one proportion test example using a polling result or a survey that was conducted. So in order for new antibiotics to be developed, it would make sense that we need chemists or scientists that were studying chemistry. So how many scientists say they are chemists? Is this proportion increasing, decreasing, and compared to when? So Pew Research conducted a survey in collaboration with the American Association for the Advancement of Science in 2014. They want to compare results in 2014 to a prior similar survey. We can do this using the 10 steps in Daniel, and we can also construct confidence intervals on the observed proportions. In 2014, 11% of the scientists say their primary field or scientific discipline is chemistry. In 2019, that percentage was 14%. So we actually want to ask, is the current 11% less than the 14% in 2009? This is a one-sample, one-sided test. We are looking to see if something has reduced. So we're looking for less than. Pew publishes their survey methods, so you can see that this was asked between September 11th and October 13th in 2014. It was a simple random sample of AAAS members, and they were selected by participation by the staff. It was limited to U.S. members, but otherwise it was a broad definition of the scientific community. Anyone was eligible to participate with the exception of AAAS staff and institutional members. They were excluded from eligibility since they were involved in the selection of the sample. You can go to this link here to read more about the survey. There is a full PDF available. We are going to pay particular attention to the results on page 106 of the published PDF with the entire survey. And we're going to look at question 42 that asks, what is your primary field of scientific discipline? In 2009, you can see that response was 14%. And in 2014, you can see that response is 11%. So starting with step one, the data, we know that they are obtained from a sample of 3,748 individuals. 11% responded chemistry. So we know P and N this time. We could roughly figure out the number that actually answered chemistry to be somewhere near 412. But it turns out we don't actually need to know the X because we actually have the P hat, which was observed at 0.11. To look at our assumptions, we know that Pew Research published that information. Is it representative of all scientists? Well, it's a simple random sample of AAAS members. So we'll assume that it is representative of those that are in that society. And potentially you could go to that society website and determine if their members are representative of the larger scientific community. But for now, we're going to assume this is representative of scientists in that society and that they are independent. We have no evidence to the contrary that there are, say, family members in the study or that each member has answered the survey more than one time. Remember, we need to check our sample size assumption, and this is based on what we expect to see under the null hypothesis. If the assumed proportion is 0.14 from 2009, then those for observing chemistry as their scientific discipline would be 0.14 times our current sample, which leads us to just over 524, just shy of 523 expected saying they are in chemistry. Not chemistry would be the opposite. And so well over 3,000, both the 524 and 3,223 are greater than 5. So we do expect to see both more than 5 responses saying chemistry and more than 5 saying not chemistry. So we are okay with our sample size assumption and we can proceed with steps 3 through 10. Setting up our hypothesis, we want to know, is the observed 11% in 2014 a decrease from the historical 2009 results of 14%? This is what our null hypothesis would look like and our alternative hypothesis. And from there, under the null assumption, we can determine the standard error of the null. Just a quick note as to why we didn't ask if this proportion has simply changed since 2009 or if it has increased since 2009. Well, we already have our observed data, and we have observed it to be lower. So that's really the main question of interest. Is it statistically significantly lower? Asking simply if it changed would be asking if it was either less than or greater than it was in 2009. Well, we've already observed it to be less than it was in 2009, and so we would be wasting our time and our statistical power to ask the greater than side. We're never going to show that 11% is statistically greater than 14%, so we don't need to waste our effort asking that side of the question. So we already know it's observed less. Our question here is it statistically less? For steps 4 and 5, we want to take a look at the z-statistic we'll use. How will random variation affect the z-statistic? Well, if our 11% and our 14% aren't really different, we'll expect a z-statistic to be near 0, or I should say if our p-hat and our p-naught are close together, then we would expect a z near 0. A z near 0 would give you a large p-value. A large p-value would retain your preference for the null hypothesis. A large z-value will give you a small p-value, and that will support the alternative hypothesis. If what we're seeing is truly random, that is, there's no difference or no change or no reduction, then we expect to stay with the null hypothesis. Remember, our decision rule is alpha of 0.05. That's what we're going to usually use. So we expect a negative z-value this time. The reason for that is our p-hat is less than our p-naught. And so up here in the numerator of the z-statistic, we will get a negative value of 0.11 minus 0.14. So we'll actually be looking on the left side of that standard normal curve in the negative area. We will choose our null hypothesis if our p-value is greater than or equal to alpha, or if our z-score is greater than minus 1.645. We'll choose our alternative if our p-value is small, or if our z-statistic is very much less than a negative 1.645. Step 7, simply calculate the z-score. Here are the components associated with that, and we end up with a minus 5.29. Step 8, look at our statistical decision. Remember, we have a minus 5.29 as our z-score. That is less than minus 1.645. It's actually much less than. So we will reject H0 and choose the alternative. Our conclusion here would be that the 2014 proportion of people who consider chemistry as their primary area of science is lower than the 2009 response rate of 14%. The response rate in 2014 was 11%. This is our conclusion back in words. We could add a p-value to our step 10. The table in the appendix of Daniel doesn't go as high as minus 5.29, so we would simply report a p-value less than 0.0001. Or we can use the p from z calculator in Excel. You'll see here that there are 3 panels with the standard normal curve. We type minus 5.29 in the blue box. Our alternative hypothesis matches this here. Is our z-value less than minus 5.29? What is the probability associated with that? And you can see it's way over here. It's even past where this curve shows in Excel. The top result gives us a p-value of 0.0000. Recall from a prior lecture, we don't actually report zeros as p-values because this line never truly hits the axis. And so we'll report, again, a p-value of less than 0.0001. What's our confidence about our new proportion that we've observed at 11%? So we've concluded it's less than 14. How confident are we about the observed value of 11%? This time we need the standard error of p-hat because we're operating under the observed proportion or the alternative. We take 0.11, we need 1 minus 0.11, and we know our n, and we can therefore calculate the standard error of p-hat. For a 95% confidence, we're going to use a z-value of 1.96. That 95% matches our alpha of 0.05. So we want to be looking at the same region or the same rejection error of 0.05. So we'll use the 95% confidence interval. And that's going to be, because we're looking at both sides, plus or minus 11%. In this case, we look at minus and plus on both sides. So we're going to use a z of 1.96. Here's our formula. These are the components. Calculating that gives us a confidence interval of approximately 0.10 to 0.12. Just a little bit over a plus or minus 1% for our confidence bound. You can use the CI1 proportion calculator in Excel. Put your observed proportion and your observed group size in the pink boxes. That will calculate your standard error. Down here in the purple boxes are your lower and upper confidence bounds. Those are identical to what we calculated by hand. In addition, you can actually use this to calculate the z-score that you want. So if we look at put in the 0.14 here, then it will give us the z-score under the null hypothesis. And this shows the minus 5.29 that we calculated by hand, as well as the standard error that we calculated by hand for the null. So you don't actually need to do these things by hand. You can do them in Excel. Our interpretation here would be we are 95% confident that the proportion practiced in chemistry is between 10 and 12%, or you could put 10.0 and 12.0, or you could use the proportions of 0.11 with a confidence bound of 0.10 to 0.12. You will do the full 10-step write-up, including the statistical test and the confidence bound on your worksheet. So you can do these in JUMP. We've looked at calculating the z-scores and walled confidence bounds by hand and in Excel. Because we have a large sample, we can use the z-scores and the walled confidence bounds. JUMP errs on the side of being conservative, and it will give you exact binomial tests and score confidence intervals. Make sure to watch the JUMP for one proportion video to determine how to use this example to get the similar results. Both the z-scores and walled confidence intervals, as well as the binomial test and score confidence intervals, are correct. They simply have different statistical assumptions. The walled and z-scores assume a large sample, which we in fact do have. The exact and scores don't make that assumption, and that's okay. Just be clear in what you're reporting. If you use z-scores and confidence intervals, that's all you need to say. If you use JUMP, then you need to make sure you are clear that you've done an exact binomial test and you've done a score confidence interval. If you don't do score, if you do walled confidence intervals, you can just call them confidence intervals. But if you use score confidence intervals, you need to say they are score confidence intervals. The majority of examples we've looked at, in fact, all of them, have been one sample tests and one-sided tests. We've been comparing a new sample to an older assumed proportion. These are actually pretty rare in research. Usually in research, you actually have two groups, and you're going to be comparing two new groups to one another. So we'll review hypothesis types in our next lecture. We'll look at how to extend a less than or greater than test to the equal to, not equal to test, and we'll move on to testing two proportions.